Have you ever, for just a second, wished you could travel through time? Well, today, we're going to do just that. We're going to dive deep into the absolutely wild and brilliant mind of Albert Einstein to figure out how, according to the laws of physics, it might actually be possible. And no, this isn't science fiction. This is a journey into one of the most profound ideas ever imagined.
And believe it or not, it all started with this one simple question. A 16-year-old Einstein just wondered, what would it be like to ride a beam of light? This single thought experiment, this one little question, would take him a full decade to answer and would end up starting a full-blown revolution in physics.
See, the answer he finally landed on was radical. It basically said that time isn't what we think it is. It's not some constant universal clock ticking away. Nope. Time is flexible. It can speed up, it can slow down, and if you get things just right, it could even grind to a complete halt. And you've totally seen this idea in action. You know, think of the Flash or Quicksilver, when they move so fast that the entire world around them just freezes. Now, obviously that's a comic book, but the core idea behind it, that's actually rooted in the very real science that Einstein brought to light. Okay, so let's get into it. Before our brains start to melt from all the weird stuff, we need to get a handle on a basic principle of physics. It's something you experience every single day, probably without even thinking about it. It's called an inertial frame of reference. Sounds complicated, but it's not. It's the reason you don't feel the Earth spinning at over 1,600 kilometers an hour right now. It's why when you're on a super smooth flight, you can pour a drink and it feels like you're not moving, even though you're cruising at 800 kilometers an hour. As long as your speed is constant, you and everything around you are in the same frame, and the laws of physics work just like you'd expect. Okay, but here's where it gets a little trippy. Imagine you're on a moving platform and you drop a ball. From your point of view, your frame of reference, the ball just falls straight down. Easy enough. But for me, standing still and watching you go by, I see that exact same ball fall in a long curved arc. So we both witnessed the same event, but we saw two totally different things. That's relative motion. How we see the world literally depends on our point of view. So here's the deal. If all motion is relative, physicists back in Einstein's day hit a wall. A huge, universe-sized wall, and it was all because of light. They knew light behaved like a wave. But here's the thing about waves. They need something to travel through. Sound needs air. Ocean waves need water. But light travels through the total empty vacuum of space. So what was the medium? What was light traveling through? That was the big mystery. To try and solve it, scientists came up with this idea of an invisible, undetectable substance that filled up the entire universe. They called it the luminiferous ether. It was kind of their best guess, this idea that everything in the cosmos was just moving through this invisible cosmic jello.
There was just one teeny tiny problem with this ether theory. Nobody could find it. Every single experiment they designed to try and detect it came up empty. The most famous one, the Michelson-Morley experiment, was the final nail in the coffin. It just wasn't there. And this failure created a massive crisis in physics. If there's no medium, how can light be a wave?
So the ether theory was a total bust. But that failure led to a conclusion so strange, so weird, it completely shattered all the old rules. It revealed something absolutely fundamental about the universe we live in. You see, all those failed experiments, they kept measuring the exact same thing over and over again with incredible precision. And they kept getting this number, 300,000 kilometers per second. That, of course, is the speed of light. But what those measurements were telling them, well, it just shouldn't have been possible according to the old rules. And this is the radical idea that Einstein just decided to embrace. Unlike literally everything else in the universe, the speed of light is not relative. It is absolute. It doesn't matter if you're standing still or flying in a rocket ship. If you measure the speed of light, you will get the exact same number every single time. It is the universe's one and only constant. All right, this is where things get truly mind-bending. Because if the speed of light is the one unbreakable cosmic speed limit, then something else in the universe has to be flexible. Something has to be able to stretch and shrink to make the math work. And that something is time itself. Let's walk through Einstein's famous thought experiment. Picture this. You're standing on a platform and a super fast train is zooming past. Just as the middle of the train gets to you, lightning strikes both the very front and the very back of the train at the exact same instant. From your perspective, standing still, the light from those two strikes travels an equal distance to reach your eyes, so you see them happen at the same time, simultaneous. But what about the person sitting in the middle of the train? Well, they're moving towards the lightning strike at the front, so that light gets to them first, and they're moving away from the strike at the back, so that light gets to them later. For them, the two strikes were not simultaneous.
So, who's right? You or the person on the train? And here's the mind-blowing part. You both are. This is it. This is the big takeaway. If the speed of light must be constant for everyone, then our experience of time and space has to be relative. The very idea of two things happening at the same time depends entirely on how you're moving.
So if time itself is relative, what does that actually mean for us? In practice? Well, it leads to the most famous and honestly the most powerful consequence of Einstein's entire theory. It's a phenomenon called time dilation. And put simply, it means this: the faster you move through space, the slower you move through time. Your personal clock, the watch on your wrist, your own aging, it all literally ticks slower than the clock of someone who's standing still. Now, at our everyday speeds, this effect is so tiny it's basically zero. But as you start to really approach the speed of light, it becomes dramatic. If you could travel at 80% the speed of light, your time would pass twice as slow. At 99%, it would be 7 times slower. And if you could hit 99.99% the speed of light, 1 year for you would be 70 years for everyone back on Earth. You would have effectively and literally traveled into the future. Which leads us to one final fascinating thought. If time slows down more and more and more as you get closer to the speed of light, what happens when you actually reach it, when you hit 100%? Well, the math tells us that time stops completely. For a particle of light, a photon, its entire journey across the billions of light years of the universe happens in a single instant. For light, time doesn't exist.